Yeah, so for this last tutorial session today, I actually decided to take you very seriously, very literal, and go over an example of how we would derive the time evolution formulation of Einstein's equations using xTensor. So let me just post again the link to the box folder. So the idea is really that you can run the notebook as we go along. So I actually want you to do this. And I also want you to interrupt me with questions if you have any, be it in person in the lecture hall or be it online. And so let's just get started. I do not really see the chat, so just speak up if you have any questions. Okay.
Activated for the in-person audience, actually.
Say again.
So the chat is not working for the in-person audience.
That's right. That's right. But I'm also, since I'm sharing my screen, I don't really see the chat. So if anyone who is online has a question, I would suggest if you can just unmute yourself and ask your question. Yeah, and whoever is in the lecture hall, you just speak up. I think I can hear you fairly well in the room. Okay, and as I said, so the idea is that we pick up on the lectures, the theoretical lectures that I gave last week on Tuesday, where I went over a few theoretical concepts that we need in numerical relativity, and I would like to show you how you can use xTensor, which is a free package for Mathematica, to actually perform this decomposition. So I hope that you managed to download the package. Here's the website is just xAct.es, and you can get the xTensor xAct package for free. Now, a few notes on notation before we get started. So if you want to denote a tensor, and I hope you can see my mouse here. So if you want to denote a tensor with lower indices, you would just use the name of the tensor, and then the indices are indicated by -a, -b, etc., etc. Whereas upper indices are indicated just by name of the tensor, and then you have your brackets, and you just label the indices like so. I will use the symbol G to denote the space-time metric, and I will use a signature -+++. I'm introducing a unit normal vector onto our spatial hypersurfaces as n, and the induced metric on these spatial hypersurfaces I will denote as gamma, and I'm using geometric units throughout. Okay, so let's get started. So to load xTensor, you will just follow this first command here. And we also load this package expression manipulation. This will help us to simplify some of our expressions. And I'm also specifying the following notation. So one is about the output for indices. Then my extrinsic curvature will have the sign -1. Remember, on Tuesday we said this sign of the extrinsic curvature is a matter of definition. So I will choose -1 such that our normal vector is future directed, and likewise the acceleration will have a sign -1 as well. Good. So with all of that set up, we can actually start and define our manifolds and metrics. So let's do that first. And the very first thing I'm doing here is actually defining a list ranging from essentially a list of indices. And I'm using lower letters A to M for my index list. I'm then defining a manifold here. I'm labeling this manifold as capital M. I'm saying that my manifold should have 4 space-time dimensions. And I'm giving this the list of indices that I just defined here. Now, I can also define my metric, so def metric. The signatures -+++. That's what I'm indicating here in this first entry. The symbol is, or the name of the metric will be a G AB. I use capital CD to indicate my covariant derivative with respect to this metric, and I will print out the metric just as G here. And as I'm executing this command, I get a bunch of other tensors defined that correspond to this metric. So I have my Helvi Witek tensor, I get my covariant derivative, I get torsion tensors, Christoffels, Riemann tensors, etc., that are related to this metric, and any of these tensors, depending on or with respect to my metric G, will be indicated by this capital CD that I used for my covariant derivative. So we have all of these quantities defined here. Good. The next part, I will just define a few more tensors. So if you're not familiar with xTensor notation, let's just have a quick go through here. So I define my tensor like so. The Lagrangian is actually a scalar. So here I have empty brackets to indicate that's a scalar, and it's defined, the tensor is defined on my manifold M. So this is, I will use for my Lagrangian and my action. I'm then defining tensors for my, so TMN is for my energy momentum tensor, has indices A and B. It's defined on the manifold M, and it's a symmetric tensor, and I can define it like indicated here. And similarly, I'm defining a bunch of tensors that will later become our equations of motion. I'm not going to go through the notation again. I can also define a constant symbol. So for example, I'm defining capital lambda for my cosmological constant, and I'm defining a coupling constant for the gravity part like so, and then actually define a rule that this should be a 16 pi.
Yeah. Why do you need to define a constant? Yeah.
So for example, if I have my cosmological constant, this is a constant, right? It's not a scalar. So I make this explicit and say, define this as a constant symbol.
But I mean, if you just input it in Mathematica as lambda, it would just assume it's a constant. So what's the game?
Oh, so this is specific for xTensor, right? So if you so it basically, to have a clean calculation, you want to make sure that you define your quantities either as a tensor or as constants. You don't have to do that, but then xTensor may complain if you're trying to simplify later on, and if you want to canonicalize your expressions. So this is xTensor specific. Okay.
Okay. Thanks.
Yep. Okay. So let me just go through here. Good. So now our tensors. The next one we need is our tensors and vectors for the 3+1 decomposition. So I'm defining the tensor, the normal vector here. Again, defining as tensor, living on our manifold M. I'm using this expression to indicate that whenever I see the contraction of the normal vector with itself, it should immediately replace it by -1, which is a normalization that we use for our normal vector. And then I can define an induced metric. So that's what I'm doing next here. Again, I define a metric. Now my signature is +++. I'm giving it the name gamma AB. The symbol for the covariant derivative for my induced metric is lower letters CD. This is just some representation, so I can use as print out the symbol D for my covariant derivative. And then it's important, since this is an induced metric, I can actually tell xTensor to can tell the xTensor and say, okay, it's induced from my 4-dimensional spacetime metric G and the normal vector N. And this is just print out here. And then I'm actually also defining another rule where I say that whenever you encounter, or when I have my projector indicated as projector, I actually want this written out as being the induced metric.
So you have this something which looks like an error message. Have metrics, there are already metrics, GG.
Yes, so this is. Yeah, so this is just a warning because we already defined our metric G on the same manifold. right? So this is just warning me that I already have other metrics defined here.
I mean, so here, GT is on the same manifold, speaking not a metric, right? Because in 4 dimensions, it would actually have a
That's right.
plus. So
that's right.
Still considered as a metric, this gamma thing?
Yeah. And it's considered as an induced metric, so it actually knows about the relation between our 4-dimensional spacetime metric G, this induced metric gamma, and the normal vector. And it's still considered as a metric. So you can use this to raise and lower indices of quantities that are defined with respect to this metric. And we will see a couple of examples of that later on.
So this is like writing G mu nu as with adding subtracting an n term. That's the point, even if it's in the upper version or something like that.
Can you say that again?
Yeah, well, probably it's difficult to say exactly, but I mean, so you can write, say, G is the space-time metric, and gamma is the space one.
Mm-hmm.
You can write it in tensorial form as G mu nu is gamma mu nu plus n mu n nu.
Okay, so exactly. So you can do exactly that, and let me just.
And then you can raise the indices on gamma using G. That's the idea. Because that integration you can write in both.
So you can write it. So let me just give you an example. So I hope you can see I'm in this line here. So if you say I have my metric GAB, and now I want to go from the metric to the projector. That is exactly the transformation that you just said, going from my 4-dimensional spacetime metric to the induced metric, but in using all indices. Then we can use this command, and this is exactly what you just said. So we can write our 4-dimensional spacetime metric as gamma AB, the induced metric, minus NA and B. So this is a normal vector.
And you can do it with both indices up as well, right?
You can also do this with both indices up. Yeah, there we go. And if you have the mixed indices, you just get your, this is just the delta. Okay. Yeah, but you can do this as well. So it knows how to do this. And it does treat the induced metric also as a metric. And as I said, so we will see that later on when we actually go to the decomposition. Yeah. Okay. Do we have any other questions here? Okay, so if not, then let me also introduce a lapse function alpha. And I will actually, so I call the lapse function, alpha. Usually I know that some people may call it capital M, capital N, numerical relativity. We typically use alpha here. And I'm also providing a rule that replaces the acceleration with respect to n with this expression here, which is 1 over alpha times the covariant derivative of alpha, which you can derive in just a few lines, if you like. So this is just a matter of taste. I prefer this form to using the acceleration. Good. So these are our 3+1 quantities. And let me define one more thing that I will use later. So I will provide a rule. So first of all, I will introduce a time parameter. So this I'm doing here. So I'm defining a parameter that I call t, which will become my time parameter. And I'm also defining a shift vector that I call beta. And here you already see one of the things that, where raising indices with gamma will become possible, because here we know that this shift vector is by definition orthogonal to the normal vector. So I can actually add that to the definition of this tensor, that's orthogonal to our normal vector. And it's so the shift vector is projected with our projection operator / induced metric gamma. Yeah, and we can make this explicit here in the definition of the shift vector. And here I'm just defining a rule that I may use later on, where I say when I see a Lie derivative with respect to the normal vector and I want to make the time derivative explicit, I will just apply this rule. And we will see that towards the end. Okay, so this is just setting everything up, defining all the tensors and parameters and constants that we may possibly need. So let's first actually derive our Einstein's equation from the Einstein-Hilbert action. I'm defining a couple of rules and substitutions here that I'm not going to go into. You can just evaluate these cells here. And instead, I want to go to the next section, define Lagrangians and the action. So we have the Einstein-Hilbert Lagrangian here. Let's define it together with a cosmological constant. And here, so I defined the symbol for my Lagrangian earlier. Here we have the Ricci scalar, and this capital CD indicates that it's a Ricci scalar with respect to our four-dimensional metric, where I labeled the covariant derivative as capital CD. And here we have our cosmological constant term. And now I can define the action, and the xTensor notation for the action is a little bit funny because it doesn't carry the integral. So you have to remember that the integral is here. Yeah, so here we have our, if I'm going from right to left, we have our Lagrangian here. We have the square root of minus the determinant of our metric. So that GG is just the determinant of our metric. And the integral is not written, but it's implicit here. And that's how I can define my action, as usual. So this is just what we are all familiar with from, Introduction to General Relativity in a slightly different form. Okay, so now that we have our action, let's actually derive our equations of motion. And yeah, so let's just start here. So we have our action that I just defined. Now, if I just take this action, which has a Ricci scalar, and I try to vary that with respect to the metric, it actually won't do the variation. So I have to trick it a little bit, and I have to say that it should write out the Riemann tensor and any contraction thereof in terms of my Christoffel symbols. And that's exactly what I'm doing here. It should be highlighted in green. So I'm applying this command and say Riemann to Christoffel. And I have one more simplification that I say no scalar, which essentially means that it for any pair of dummy indices, it actually introduces a new letter here. It's just something that I find more useful. And this is the first step that you can do to derive your equations of motion. So this is just writing out our action in terms of Christoffel symbols. And now I can actually go ahead and perform the variation. So again, let's go from the inside to the outside. So we have on the right-hand side here our action written out in terms of Christoffel symbols. And now I can say vary. So the command to do this is var_d. So vary with respect to my metric GAB, this action here. So this is a core command. And then I'm just dividing by the square root of minus the determinant of the metric and expand to simplify a little bit. So this is a next step here. And now I need to get back from the expression in terms of Christoffels to an expression in terms of the Ricci tensor. And I defined a command to do this myself. I think newer versions of xTensor or xAct may actually have a new command to do this. So this is what I just derived. I'm applying the rule that I've defined myself. I'm simplifying, and an xTensor or an xAct, if you apply this command simplification, it actually knows about how to simplifying tensors and how to canonicalize these tensors. And that's why I'm defining every quantity that I'm interested in, either as a tensor or as a constant, because then I can use this really nice simplification command, which is much more powerful than the simple simplify that you have in Mathematica. Yeah, so here, this one already knows about how to simplify tensors. And if I apply this, actually I should also execute all the commands so that I'm all with you. Yeah, and then we get Einstein's equations with a cosmological constant in vacuum.
Question. So this var d gets rid of this second derivative integrates by parts. That's what it happens.
Yeah, so that's right. Yeah, so if you so this is that's what it does.
So if you just used any stupid Lagrangian and just take
so
scalar to power 25, it will also
say again. So if I use what?
Take the Lagrangian displacement scalar to power 25. And you have a lot of high order derivatives. It's going to integrate everything by parts.
No. So I think so. I mean, I didn't go that crazy, but you have to work a bit harder to actually get this. Yes, I mean, it's enough if you go to things like Riemann squared, and you have to work a bit harder to get all the integration by parts that you need.
Thanks.
Yeah, sorry to disappoint, but yeah.
So can you just explain again what the no scalar is doing after the Riemann stuff?
Yeah, so you know what? Why don't we just look at what happens if we don't have the no scalar, right? So let's just take our Einstein-Hilbert action and let's write out the Riemann in terms of Christoffels. So what you're getting here, so this is highlighted in these red brackets here, is essentially an expression that uses these dummy indices A, B. So here, it's actually not that obvious here. Let me think about a simple example. Okay, so let me do the following. Let me take this GAB, our metric, and Einstein-Hilbert action. So essentially what we have above. And let's also take, so this is just writing down, so I mean, nonsense quantity, but this is just our action times the metric. Let's go to the Riemann to Christoffel, because then you see what it does here. So it has in the brackets an expression that is summed over all the indices. So, and it says, oh, I can here use as dummy indices A, B, C, and D. But then, of course, my expression that I have in front, the free indices are also A and B. Now, as long as it's in these red brackets, in principle, xTensor knows that these are the dummy indices, but I don't like this. So if I look at an expression, I want to see at a glance what are the dummy indices, what are the free indices. So I prefer to use instead the no scalar, and then it will just label. So it will not double any of the labels. So in particular, will not use the free indices to also label a dummy index. Okay, and I mean, this is just personal preference, but you have this command to do this.
So could you just show us what would happen if you take the Ricci scalar square as Lagrangian? What will happen?
Can we do that at the end? So I would just go through this, and so what I would suggest, if you have time in the end, we can do that together.
Okay.
Yeah. Otherwise, you can. You're welcome to use my notebook and play around with this at the very end. Yeah, because what I actually wanted to show you was how we, once we have the field equations, how we actually do the 3+1 decomposition as follow-up on my lecture from Tuesday. So please keep your question until the end, and we can think about this a bit more. Okay, good. So let's see. Oh yeah, so the last bit that I had here in this part was just to add the energy momentum tensor. So, and I'm adding that here by hand at the end of our equation. So we have our field equations in vacuum minus the, and my notation here is such that any equation of motion is defined as quantities equals to 0. So that's why I have the energy momentum tensor here on the left-hand side. And the reason for me is that if I now start manipulating those expressions, then manipulating a 0, I can make fewer mistakes than having to keep track of the left-hand side and right-hand side separately. Yeah, so this is just to reduce possible errors. And then I'm also defining the trace reversed version of the field equations. like so. And yeah, so these are our field equations. So let's start with, so let's not go over the projections of the energy momentum tensor. We can just evaluate this. And we can continue down here with the decomposition of our tensor field equations. And again, I'm starting by just defining a few tensors and substitution rules. So we have one set of tensors for our field equations for the decomposition. We have here tensors that will become our Hamiltonian constraint, so suggestively labeled as H. We have tensors that will become our momentum constraint, labeled as curly M here. And again, this will be one that is orthogonal to the normal vector and projected with our projection operator. And we have a last set of tensors here, curly P, that will be the completely spatial projection of our field equations. So that will give us eventually the time evolution equation for the extrinsic curvature. And again, for this last one here, I'm defining it as being a symmetric tensor. Just as a side note, you can also, if you're so inclined, if you have a tensor that's anti-symmetric, you would equivalently put here anti-symmetric and then the indices in which it is anti-symmetric. And in principle, you could also define a tensor with, say, 4 indices that obeys the symmetry rules of the Riemann. Okay, then this tensor here will be orthogonal to our normal vector, and it will be orthogonal in both indices, and it's going to be projected again with our induced metric. So let's define those. And here are just some auxiliary tensors that I will use later to indicate our time derivatives. Good, that's defining our tensors. I'm not going into detail about the simplification rules, but you can just evaluate those. And now we will go over the derivation of for the different equations in our 3+1 system. So the first one here is, well, not actually a derivation, more for completeness, so that I have everything in one notebook, giving me the time evolution equation for my metric. So here I'm basically subtracting so I have the Lie derivative of the 3 metric along the normal vector. So that's the notation here. Yeah, so I have Lie d indicates the Lie derivative with respect to the normal vector. This is my first entry, and then it's acting on my induced metric. And I'm just subtracting essentially the same expression, but expanding out what the normal vector is in terms of the time parameter, the time vector, and my shift vector. And I'm, as I said, so this is more complicated than necessary, but will give me just the time derivative of the metric, which is given by -2 times the lapse times the extrinsic curvature, and this k gamma AB here is the extrinsic curvature with respect to my induced metric. And then we have here the second part is a Lie derivative along the shift vector of my 3 metrics. So this is just the kinematic relation that I get from just introducing the extrinsic curvature, as we've seen on Tuesday. So this is just kinematics. So that's something that you would usually get. So let's look at the field equations. And before we can actually, so the first step that we would do here is actually write out our field equations in all projections along the normal or onto the hypersurface. So either contracted with a normal vector or projected with an induced metric. And we can do that by applying this induced decomposition here. And we are applying that on our field equations that I've defined previously. So I say, and performs induced decomposition with respect to my induced metric gamma and my normal vector n. Do we have a question? Okay, we can also, so the next step that I'm then doing is to say, actually I can also maybe just do that in the line above to go over this step by step. So if I just apply this first command here, what I will get in principle is the different, as I said, the different projections, and in general, the projection operator would be indicated by this P gamma here, acting, for example, on our four-dimensional Ricci tensor. Then we have this mixed projection here, one index contracted with a normal, the other one projected with our projection operator. Now, I'm not a big fan of this notation, so I will actually say, okay, whenever you see this projection operator, please replace it with my actual induced metric. So I've defined this rule further up. So, and now whenever it sees this projection operator, it would just replace it by our induced metric. Then here again, we have this weird notation where dummy indices have the same label as free indices. I'm not a big fan of that, so I say use a no scalar, so we can get rid of this. And then we see, for example, if we compare these expressions here, that we still have both the four-dimensional metric and the induced metric. So I want to focus on one of them. So I will replace, whenever I see this metric, the four metric here, with a relation to the induced metric and the normal vector. And that's what I can do with this metric to projector. So now all our expressions are carrying either normal vector or projection operator with them. And we can just bring that into canonical form. So that's what we have here. And to make our life a little bit simpler, I'm now focusing on vacuum spacetime. So I will just put the energy momentum tensor TMN, sorry, to 0. And that's what I already had here in this line. Okay. So the next step, you see that now what we have here in these expressions are our normal vector, our induced metric, but our Ricci tensor and Ricci scalar is still the four-dimensional one. So we now want to use the Gauss-Corazzi relations to actually express the four-dimensional Ricci and tensor and scalar in terms of the three-dimensional Ricci tensor and scalar and the extrinsic curvature. And that's what I'm doing here in the next step. So I'm taking my previous expression that I defined here, and I'm now just applying the Gauss-Corazzi relations to do this. And again, if you want to see what's happening here step by step, we can actually also just do this. So this would be the general expression. Again, not a big fan of this projector or using the same label for dummy indices as for free indices. So let me just get rid of those. Okay. Let me also already simplify a little bit. Good. So we also still see some expressions. Oh, let me see. Yeah, so the other one that I will also use is to say that I want to, again, replace whenever I see my four metric with the projection operator. And sometimes you may also still have expressions that involve the gradient of the normal vector, which we know is related to the extrinsic curvature. So I will also apply this. So I can replace the gradient of the normal with the extrinsic curvature. And again, xTensor has already defined those relations. So I'm using that here, and I can do some simplifications. And this is essentially what we have here in the next expression already prepared. So that's what we have here. So now we have our field equations expanded in all possible combinations for the projections was either along the normal or the induced metric. Yeah, so remember last week on Tuesday, we said if you have a vector or a tensor, we can write it, expand it out in all terms that are either contracted with a normal or projected onto our hypersurface, or any mixed projections thereof. And this is precisely what we're doing here. I'm doing precisely the same, but I'm not going to go into the details for the trace reversed version of our field equation. So this is done here in this second command. So I'm just executing this. And now we are ready to look at the different projections in more detail. So let's take our lengthy expression that we just derived and contract it in both indices with a normal vector. So this is essentially what gives us a Hamiltonian constraint. And if I do this, so this is what I have here in the first steps. I actually already printed out all the details. Here we see our three-dimensional Ricci scalar now with the D indicated as being the Ricci scalar with respect to the induced metric. We have our extrinsic curvature here. And we still have one derivative that we may not like completely, because here we still have a four-dimensional, so covariant derivative with respect to the four-dimensional metric. So we want to get rid of this one, and we can do replace this by applying this command to induced derivative. So to induce derivative from our four-dimensional covariant derivative to our covariant derivative with respect to the induced metric. If we do that, this is the result that we get. And here we have this gradient or derivative of the normal vector. We know that this can be related to the extrinsic curvature. So I'm again replacing this with extrinsic curvature, do some more simplifications. And now we have the usual expression of the Hamiltonian constraint in terms of the three-dimensional Ricci scalar and the extrinsic curvature, and this indicates the trace of the extrinsic curvature. Good, so that's our first constraint equation. Now to get the momentum constraint, we want to contract one of the indices of our field equations with a normal vector, and we want to project the other one, the other index with our projection operator or induced metric. And that's precisely what I'm doing here. So I'm again using this field equation that I've already decomposed into all its components, and contract one of the indices with a normal, project the other one with our projection operator, and just have to do some simplification. And we already get the usual expression in terms of the divergence of our extrinsic curvature and the derivative of the trace of the extrinsic curvature. Good. So these are the constraint equations. And then the last set of equations that we need as our evolution equation for the extrinsic curvature. And we get that by projecting our field equations onto the hypersurface in both indices. Okay, and actually what we can do here is, again, go step by step from the inside to the outside. So we have here our field equation. Now here it's advantageous to use the trace reversed form of the field equations, and we are projecting them onto the hypersurface in both indices and perform a simplification. And yeah, as I said, let me just do this here. You can see step by step what's going on here. So we have already our three-dimensional Ricci tensor, or extrinsic curvature terms, but we still have some not so nice terms here that involve the covariant derivative with our form metric. So I'm doing one simplification that brings our projection operators inside here. So that's one of the simplification rules that I've defined earlier. And I'm simplifying again, and I think this is a nice form. So what we have now here are covariant derivative with respect to the 4 metric acting on the extrinsic curvature, which if we look at this term and you're familiar with the Lie derivatives, is quite suggestive that this will give a Lie derivative with respect to the normal vector of our extrinsic curvature. And we also have these terms here that will actually, and again, so if you look at this term carefully, you see that this is suggestive of being a Lie derivative along the normal vector with respect to the induced metric. And that's indeed what it is. And what will happen in the next step when we go from the 4-dimensional covariant derivative to the induced derivative is that these terms will be replaced by the Lie derivative along the normal vector, and that acting on the metric we know is the extrinsic curvature. So these terms will be replaced by terms involving the extrinsic curvature. So let's look at this. So we have the 2 induced derivative of the whole expression. We want to go from the 4-dimensional covariant derivative to the 3-dimensional one. And here you see precisely this replacement, and all these terms that I just said should become extrinsic curvatures R. And then in this last bit here, we have our Lie derivative along the normal vector of the extrinsic curvature. Now we still have some of these terms that are derivatives of the normal vector. So let me replace this with the extrinsic curvature so that we have consistent notation and simplify a little bit. And now we have precisely the expression for that will give us an evolution for the extrinsic curvature here in this term. Okay, good. We have this, and now what I'm doing here is just taking those expressions, replace the Lie derivative along the normal with a derivative along the time parameter and our shift vector, and then I will solve for the derivative along the time parameter. And this now gives us the time evolution equation for the extrinsic curvature here. Yeah. And these are probably the equations that you might want if you want to write down the ADM-York type equations here. So one last thing that may be quite useful is that if you have derived those equations, you may want to put that into a set of notes or a paper, so you can actually output those as TeX files. And that's what we'll do here in the last bit. So we will load this package, also part of the xAct bundle. It's called xAct. And if you do that locally in your own folder, you will have to adjust the path where you want to export it. But here what you're saying export, it gives a path name for the file. And then the last bit here is the name of the file, .tech. Print of the expression. Remember, we defined or derived our Hamiltonian constraint as the curly h, and we have the text here. I'm doing this for all of these, all of the quantities. So Hamiltonian momentum constraint, also here for the evolution equations for the 3-metric and extrinsic curvature. Okay, so this is in a nutshell how you can perform a 3+1 decomposition of Einstein's equations using xTensor. And I think with that, I'm actually at the end of this part. So if you have any more questions, or if you want to play around a little bit, I can, we still have quite some time. So, yeah.
Well, I still have my question, but maybe this is for later or
as you like. So, I mean, if anyone has any other questions, or otherwise, as I said, so you're most welcome to also just play around with it. And see what happens, right? So, does anyone else have a question first?
Can you say again how to save it to TeX?
Yeah. So you see, so you can still see my screen, right?
Yep.
Yeah. Okay. So you will load this package here, which is called xAct. Then the notation here is the following. So you have export. You give the folder. So in my case, this is the path where I want to have my file, right? So this is a file name, including the entire path here, just for me to make sure that I'm in the right folder. Then I have here the so here's the quantity that I want to print out as tech, and I say tech print this quantity as text.
Sorry, my question. So GRSplit is your notebook, or is it another file?
Oh, okay. So this is just my folder. So this GRSplit is actually a folder, and then this is a file name.
So this document already exists.
So that exists for me. This won't exist yet for you. Right?
Okay. Yeah, that's what I want. So we need to create a file and save it.
Exactly. So if you want to try this, you need to change this path here, right? And then if you want to give it a different name, you can also give it a different name. But yeah, so this is the folder that I have here locally on my laptop. Yeah, and if you just give me a second, I can actually also open this so that you can have a look at what this looks like. So let me just stop sharing, because I think I will have to share my entire screen if you want to look at my file. So let me just do this. Okay, now you see the entire screen, and you should be able to see my terminal here. Yes, can you give me a quick yes or no?
Yes.
Okay, good. And let me just make this a little bit bigger. So can you also see, is it large enough to see?
Yes.
Okay, good. So here you see, so this is my folder, right? So presentations for this year, for the school, and I've created a folder for where I want to output the files. And since I already ran the commands, the files are now already here. So let's have a look at the first one for the Hamiltonian constraint. And so this is the output that you get, right? So it has the -2, so it knows how to typeset Greek letters. The only one that's not so nice is that the extrinsic curvature with respect to the induced metric was labeled K gamma, and that's exactly what it prints out here. So you may want to change that afterwards, or massage your expressions a little bit if you want to have slightly different output here, and then you have the indices and everything in basically in LaTeX script. And I do find that quite useful if you have lengthy expressions. Here.
Sorry, I think that your screen is freezed now. Or...
Frozen? Okay, let me stop sharing. Let me share again. So, okay. So can you see my terminal?
No,
Not yet.
Yes or no?
No, not yet.
Not yet. Okay. That's weird. So let me just try again. Still no?
Now, yes.
Now you do? Okay, so you should actually see my entire screen here.
Yeah.
So what was the last thing that you could see?
We couldn't see the file, like when you did the
API part. Okay, so can you see what's printed out now?
Yeah, now, yes.
Now you can see, okay. Yeah, so let me explain again. So yeah, so you have here the printout, for example, of Greek letters. You have the indices here, and as I said, so the only thing that is not super nice is maybe this one here, because if let's just Can you still see everything?
We only see we see your terminal.
Yeah,
Oh,
now
you see
it
it.
works.
Yeah, so you do see the terminal. And let me just, for comparison on the left here, take my Mathematica notebook that you also should be able to see.
Yeah.
Yeah, okay. And let me just print out what our Hamiltonian constraint is that we derived, right? So here we have the cosmological constant term, our extrinsic curvature. And as I said, so the notation here is K gamma to indicate that this is the extrinsic curvature with respect to the induced metric. As is here, and this is our Ricci scalar. So the equivalent expression now here on the right in the terminal in the TeX file is precisely this, right? So we have our cosmological constant term. This is our extrinsic curvature, and that's where I say, so I sometimes, don't like in this form, so I would massage the expressions a little bit in my Mathematica file before actually outputting it as TeX. But you do get all the indices, including the ordering, as you can see here in your TeX file. So I find this quite useful.
But each equation is one TeX file.
So here we have, so this one that I'm showing you here is a Hamiltonian constraint. So essentially exactly this expression that I have here on the left, printed out as TeX format. So this is a very, so here in this export, this is the very first print out in a TeX format. Oops.
But can you put all the equations in a single file?
You probably could. I haven't. So what you probably would have to do is change this TeX print here. I haven't done. So I usually have the expressions in a separate file, but I'm sure you could also do this together if you modify this part here. So again, it's one of those things, just play around with it. Yeah. And again, maybe to remember, at least for me, all the expressions that that's not true. So we have the constraints here, and then for the time evolution equations, what I have is essentially just the right-hand side of my equations. So this is what you would get here in the example. Okay. Good. Any other questions? Okay, so let me stop sharing. And then I guess a question for the organizers. How much time do I still have?
You have 20 minutes.
20 minutes. Okay, so because we had this question in the audience about what happens if I have a Ricci squared in my action, or a Ricci to the whatever power you want. So again, so as I said, the first thing is I would invite you to actually play around this yourself if you can. But we can also try to have a look at this here. So, and for that, let me share again the screen. Unless, of course, we have any other questions before we try to do this live. Okay, so what we wanted to do here was to take, what was it, Ricci scalar 2, which power was it, the squared?
Yes, for example, yeah.
Yeah, as an example. Then we also have here our minus determinant of the 4 metric. Okay. And so the first part, as I said, if you want to vary this with respect to the metric, so let's actually just do this. And you will see A, B, and here we go. So if we do this, then it actually will only vary my determinant of the metric, but it actually won't do anything to my Ricci scalar. So we have to expand the Ricci scalar in terms of the Christoffels. So let's do this next here. So this would be just Riemann Christoffel symbols. This is what we get. As I said, I'm not a big fan of the no scalar. So let's see if we can still work with this. Yep. And let's now try to do the variation. And what you will get here are these expressions. And I mean, this is not particularly obvious. And as I said, so this would be a stage where I would probably mix using xTensor with actually doing calculations with pen and paper to see where we may have to impose partial integration. So let me just try to see if we can make this a little bit nicer. Okay.
You do simplifications on this, would this help?
Not yet. So I'm not doing a simplification just yet, because if you look at these expressions, it's a bit lengthy, but if you look very sharply, you will see that there are expressions that involve partial derivatives. Well, partials acting here are not tensors, right? So if you now were to do a simplification, xTensor will complain that you're trying to do a tensor manipulation on objects that are not tensors. So you see what you would get these. So it says incompatible derivatives, but really what this means is that you're trying to do a tensor simplification on objects that are not tensors. So it gives you a warning to indicate that that's not quite correct yet. So we have to work a little bit harder here. So the first thing that I would try, because I have already defined some simplification rules, would be a rule taking gamma to Ritchie's. Let's see whether, and we have these replacements here. This is good.
Sorry, it got frozen again. The screen got frozen again.
Oh, I'm sorry. Let me save this and let me stop sharing for a moment and let me get back to it again. I'm sorry. So I guess Zoom is not very cooperative now. Let me just try to share again. Good. Can you see it?
No, not yet, but
Okay.
it takes some time.
Maybe to take some time. So just give it a moment. So it does indicate that it's sharing here, but if it doesn't, it may just stop again. So is it showing up?
Yeah.
No. Okay, still not? Okay, let me stop. Oh, I'm sorry about this, but you know what? So you should have access to my notebook, and it's in the box folder. And I actually put the link again in the chat, and it's also on the website. So if we cannot get it to work again, then you can also just try it at home. So let's try one more time. So to share screen and Zoom, please work with us.
Oh, yes.
Oh, yes.
Hey, success. Very good. Okay, so where were we? Okay, so I'm not sure what the last bit was that you could see, but here was the expression that we were trying to manipulate, right? So we had this Ritchie scalar squared, and we wanted to vary it with respect to our four metric. So I did apply one rule here that I had predefined that basically knows how to go from the Christoffel to the Ritchie, and we see we have part of some of these substitutions here, but it's not complete yet. And we still have, as you see, we still have some of these partial derivatives here that are not very good if you want to actually apply our simplification rules. So, you know, what I do next is the following. So I can change my covariant derivative. So I can change my derivative from the partial to my covariant derivative, because then if I do that, I know that I'm again manipulating tensor expressions. So I change covariant derivative. on the entire expression, and we go from the partial derivative, and the partial derivative is indicated by a capital PD, to our covariant derivative that we labeled as CD. Let's do this. And now we see that all the partials have been replaced by this covariant derivative here.
It goes again.
And it's frozen again. No. Oh. But so I think instead of going,
that was very helpful. Thank you.
let me just stop here, because I think at this stage, so I think you have a starting point, and you will have to do some simplifications here. But again, the other point is that if you see terms where you need to apply partial integration, you may have to trick it a little bit, right? So when I looked at some of these quadratic gravity theories, I had to massage the equations a little bit to actually get all the partial integrations that you can get for the simplification. Yeah, so keep that in mind if you want to look at one of these to whatever power you wish to look at theories. Okay, so I think I would stop here with the regular tutorial. Do you have any other questions or any other comments about this?
I would like to ask something.
Mm-hmm.
In your first lecture, you mentioned the pieces and formalism. Can you use the xTensor to get a conformal transformation and then define? Okay.
Yeah. And indeed, I mean, I don't have it in this notebook, but for example, yeah, so when you want to derive the initial data, or if you want to derive the BSSN equations, that's precisely what you do, and you can define that. So so the strategies that I would apply here is that you say you define your conformal factor. You define, well, first you would define another induced metric, right? Because you would have another metric that's basically conformal to your induced metric. You define your conformal factor. If you want to split your extrinsic curvature in trace and trace-free part, you would define that as well. And then you have, so once you have those, the way I go about is that I actually define replacement rules for my tensor so that I can perform the conformal decomposition step by step. And there you may want to, so you want to be careful when you do that. And that's because of Mathematica notation. So, if you define these rules, then so it will replace whatever you have in your index list. And in particular, so you want to be careful how you define your transformation for lower and upper indices if you have different factors there, right? So if you apply your replacement in the wrong order, you may end up with the wrong power. So you have to be a bit careful, and to get practice, just take a transformation that you're familiar with, where you have done the calculation on a piece of paper, and then check carefully. But yes, this is what you could do. Yeah.
Now let's start the speaker again.
Okay.